Hey guys! Previously we did text classification using both a dense network with only encodings and one where we used embeddings. However, our models did not take the sequence of words into consideration. As a result, did not factor in meaning. Now we're going to take a look at recurrent neural networks, or RNN. An RNN is one in which the output gets put back into the network along with the new input. If you look at the image on the right, the red circle is the input layer. Blue circle is the hidden layer. The black is the output layer. The recurrence means that when the output is produced, it's added to the input for the next circle. This sequence could be viewed as a series of time steps. Every instance of execution is a time step. Consider the sentence. From the moment you hear the first word, you start computing the next word, which is the output of the model. The output serves as the input for the prediction of the next word. These types of networks are suited for handling sequential input. They have different types of outputs. You can have a single output, or you can have a sequence. All this happens on one layer, and you could stack layers to produce more complicated networks. RNNs are difficult to work with. They're computationally intensive. They grow rapidly. They're prone to vanishing and exploding gradients. Gating was introduced such that not all of the output gets added to the input. Decisions can be made about how much of the output is retained and put into the input. This gave rise to several different types of RNNs, such as gated recurrent units, or GRU, and long short-term memory models called LSTM. It's also important to choose the right optimizers, more importantly, to work with a GPU. RNNs have various applications, like image captioning, where you provide an image, and the network outputs one or more words describing what is contained in the image. Document classification, where the model reads a document and tells you what category that document or the text in the document would fall into. Video classification, where the model is fed a video and learns to classify the video. Video captioning, where the model takes in a video, then outputs one or more words, telling you what's in it. Language translation, where you pass in the sequence of words in one language, and the model produces a sequence of words in another language. Text summarization, where the model will take in a large body of text and output a smaller and more compressed form, containing roughly the same amount of information. Forecasting, where you pass in some numeric information, like the price of a stock, and the model outputs the next phase, where it predicts the price. TensorFlow implements RNN as several layers: RNN, GRU, LSTM. All these support something called a bidirectional layer. It lets the layer analyze the input in both a forward and reverse direction, letting it better capture long-term dependencies. Let's go back to our code and see how implementing an RNN impacts our accuracy. Back in our notebook, we need to go to the menu and set our runtime to make use of a GPU. This will speed up our training considerably. We can then install TensorFlow and import our dependencies. Next, we import our dataset and pre-process it. We implement an embedding layer in our model with a dimension of 16. We can look at our model summary. We have 326,000 parameters. Then we can compile and train it. This model has a similar number of parameters to the previous one. We can go ahead and train our model. We could swap screens to compare the result of our training. While it takes longer to train RNN, even with a GPU, we could see that we get a much better accuracy. After the first epoch, we get 81%. After the 10th, we get 99%. Without any optimizations or performance tuning, we got better accuracy from the RNN. In the next video, we're going to look at using convolutions for sequence models.